Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming to you from the Mozaic Works studios, and what I have for you today is a deeper conversation about inheritance. And by now you are probably wondering what is to say about inheritance. Generally, when I'm discussing inheritance or when I hear people discussing it, it's one of two camps. It's either that you should never use inheritance, that you should use composition instead. And indeed, most of inheritance can be replaced with composition. Or something like, yeah, we can use inheritance. We already have inheritance in our systems and we are using the same patterns, but often we are not so happy with it. So I was somewhere in the camp of favoring composition over inheritance. Is something that I've done for many years, because in the beginning of my career, I would be doing in C++ and then in C#, we would be having a lot of deep hierarchies of classes. And those were not very easy to change, and if you got the wrong abstraction, you'd end up with problems and so on. So when I heard about this advice this piece of advice that you should favor composition instead of inheritance, I thought, yeah, that makes sense. But then this was, I think, a few weeks ago. Time passes very quickly. This conversation was started by Samir on Mastodon. And you know Samir, I've interviewed him here for related to his startup adventures, and it was a very interesting interview, which you can check out. But in this case, he was asking about something that looked like a specific problem related to inheritance. When you have an object-oriented type hierarchy, I have found that you either want to call upwards, subtypes calling functions methods on supertypes, or downwards, supertypes calling abstract functions methods on subtypes, but never both. In my experience, if you have bidirectional communication across the type hierarchy, you tend to have a bad time. Has anyone on here encountered the same issue? Is it a real issue or am I imagining it? Is there a name for it? Come across any articles? And already it's interesting because of the way he was stating the problem about subtypes calling functions methods on supertypes, or supertypes calling abstract functions or methods on subtypes. And I think he mentions later on that it's more about a kind of a functional style of programming, which is, I guess, why there are these problems with inheritance. Now, the interesting part is that part of this is, so it's hard to understand, but on one hand we have a few design patterns that fit this. And I think my first instinct was to think about the template function pattern when I read this. But let's see. So there's a bunch of answers about list covariance and contravariance, list of substitution principles, composition over inheritance, and so on. And then I entered the conversation, started discussing some more. But really the most interesting part is, well, I also talked about this, that we use the ABC model, abstract interface, 1-to-N base classes, 1-to-N concrete implementation. This was quite the norm when I was programming in C++, the beginning of my career. And I think that here the goal was probably reuse for this type of hierarchies, and they were very it was easy to create them, more or less. The problem was that they were difficult to change if you had the wrong abstraction. And I guess this is the main challenge with inheritance. Inheritance is a very strong relationship, because the class, the subtype, inherits both interface and behavior from the parent class. So it's the strongest relationship, in fact, that you can have between two objects. You can have implementation inheritance, which is why we have interfaces and we implement interfaces in many programming languages. And use this is a less strong relationship, because you don't implement you don't inherit behavior. But basically you need to choose between between interface inheritance and both interface and implementation inheritance. So these are the two. And most of the times you can have the same thing implemented with composition, because you could have a class that acts kind of like the base class in the inheritance scenario, and the class that would derive from it, instead of deriving, would actually call the parent class, which is fundamentally the same thing. Now, interesting observation about, and I think we talked about this, about Liskov substitution principle. Liskov substitution principle, many people believe that it applies to inheritance only. But what Liskov's substitution principle says is that you should be able to replace a subtype with a parent type, or the other way around, without surprises. I hope I'm not stating this wrong. So, and if you want this to happen, what you need, it's not actually related to inheritance, because you could have parent types and subtypes without using inheritance. There are other ways of doing that. Even with composition, you basically have subtypes and parent types. All right, so we were talking about this, that look, just refactor inheritance to composition is saner. And Samir said, agreed, but often the language support for passing structs of functions is a lot more ugly than we would like. Also, we keep gravitating, towards inheritance. Are structs of functions objects in OP? This is basically what you can do. Right, and when you have 3 bags of functions over the same data, you tend to combine them with inheritance. I'm not claiming this is a good thing, just that our languages do make certain things easier than others, even Haskell. Now here I prefer, and maybe this is where I differ, I think, in opinion with many of my friends who gravitate towards strong typing. I think this type of problem is easily solved with duck typing. As long as I'm passing objects that look the same, why should I care whether they are the same or not? So that's one thing that I really love in Python, is that you can write different objects, and as long as they have the same functions, you can pass them to the same, you can replace or pass them to other classes or to other functions. Now, of course, there's a challenge with that because you still need to maintain some kind of coherence. But as long as these objects are very small, they will not need to change as much. So there are a lot of things that need to happen here regarding design to make this work. But this is a specific style of design that I personally love, where we have small objects very specific to a goal, and we use them interchangeably because of duck typing for different scenarios. Now, I would like to have, and maybe there is a way in Python to specify that when you call this function, this object should have these function signatures or something like that. That would be fun. That would be useful, I guess, for higher or larger code bases. If your code base is small, you can still keep this under control very easily. Or you can keep it under control with unit tests, because with unit tests you can basically check this. But what I would like to see generally is, and I think this transition has started, is this ability of having small objects that look like one another, maybe even act like one another, but the looking is defined by some kind of templates that we can, maybe an interface. I've been looking in Python how to do interfaces, and I don't find it that easy. Or some kind of definition of the initial interface. And then behavior tested through tests. This is also where something like design by contract could help, where you define the rules for the behavioral rules for the object that is passed in. Maybe another style of testing would also be interesting, one where you actually run contract tests against objects that you pass in to a function instead of the other way around. This would actually be an interesting thing to try. But anyway, he was saying, I'm not claiming this is a good thing, just that our language do make certain things easier than others, even Haskell. And I said definitely, which is why I'd like languages focused on usability. Yeah, I like more conversations around usable software design. You probably know this, but it's worth remembering that structural design patterns have two forms, with inheritance and with composition. So this is getting us into some interesting territory, and I think to me this is where things started getting interesting, because we have these design patterns that many people now are saying, oh, we don't need them anymore because they are already in our programming languages. You don't know how to use them. You still need to learn how to use them. There are two ways. Every design pattern from Django 4 has two different implementations. One is with inheritance, one is with composition. And it's worth looking at both and seeing the equivalence between inheritance and composition. And then we were paging Rebecca Wirfs-Brock. Why? Because she is an actual expert in this domain. I mean, she was doing object-oriented programming long before many of us. I think before I was born. So this is where it starts getting interesting, because Rebecca provided some incredibly useful insights. And let's see. Classes in an inheritance hierarchy can define concrete methods, abstract methods, or empty methods. Methods of any kind can also be overwritten. through carefully using these building blocks, you can build abstract algorithms or steps in a computation that either must be or can optionally be defined by a concrete class. This is a rather long explanation of the elements of building up code that actually uses inheritance this way. A good example of this style of design can be found in the Smalltalk collection hierarchy, which at the top of the hierarchy defines common definitions of various sorting and processing methods. So already, whenever you are talking to Rebecca, just as a general observation, you end up with a lot of things you want to read or learn. And this was the case for this conversation as well. So let's break this down a little bit, because I found it very interesting, and it's a different way of thinking that I was using. I was thinking more in terms of design patterns for classes, but she broke it down into design elements, into design building blocks, which is very, very cool. And so she's talking about concrete methods, so methods that can do something, abstract methods, or empty methods, and then how you override each of them. So this is one part of it, which are the building blocks. To be honest, I've never liked empty methods in base classes. I always found them weird, but on the other hand, I think it makes a bit of sense, because an empty method on a base class is like a null pattern implementation. It's like, the do nothing. It's the do nothing lambda. It's a fundamental part of many design constructs, actually. And I think if you're doing anything more complicated in software design, you end up using this null method pattern. So I used to be annoyed by that, but now I realized that actually I was being annoyed by the wrong thing. So empty methods at any kind can be overwritten. Now, interesting thing, she also mentions two specific places where inheritance is useful. Abstract algorithms, and we definitely see that even in modern types and type hierarchies and standard libraries of Java or C#, or you have the sort algorithm that applies to different types of collections, and then you have the collection class, and the collection is implemented in various different ways, and you can sort it, and some collections are sortable, and so on. So there's definitely where abstract algorithms make sense, but I guess this would make sense also for other types of algorithms that you have in your code. Maybe you can do this for things like, I don't know, login and register user and login and logout and stuff like that. This could be abstract algorithms with various implementations, like login with Google, login with... Now the problem with these things is where it gets tricky, and I think we end up discussing this as well in this thread, is when you hit the wrong abstraction. And sometimes, this is where I still don't have an answer, because sometimes you find a new abstraction comes up. Like we used to have login with user and password, right? And this was for a very long time the norm. And then we switched so that most applications use now login with email address and password. Now, is this a big change? Not really, because username, email address, you can say it's the same. But the next thing is when you have login with an external provider. Now, here's where things can start to get a little bit dicey, because now you need to call an external provider. You have additional possible error cases. The external provider is not answering. You need to refresh your auth keys, and so on. So maybe you can fit all those into one abstract algorithm. But this was always my problem with inheritance, is that it blocks you into these kinds of steps that you define once in the beginning, implement them, and they go all the way down. And then when I come and I try to implement a new provider for that thing, maybe the steps are not quite right. And I never know what's good then. Should we refactor the hierarchy? But refactoring the hierarchy is a quite complicated process, particularly when you have a deeper inheritance tree, and when you have different types of or many implementations. So refactoring is possible, but not that easy. Maybe you can, in this case, add some new steps that are implemented as null methods, as empty methods in the base classes. This is something you could do, and add additional things, additional implementations on that use the new model. So I don't know. I've always had difficulties with evolving inheritance. I think this is the challenge, and we end up discussing this as well. But so we can build abstract algorithms or steps in a computation that either must be or can optionally be defined by a concrete class. Cool. So that's interesting. Already a few clear cases and building blocks, and I really like this model. This is a model of inheritance that I haven't thought about, and it's much deeper than anything I've read on the topic. All right. And then Rebecca is returning to say, okay, I don't think of methods calling up or down a type hierarchy so much as executing a particular method that has been defined in a hierarchy. So there is Samir worded the question was hard for me to understand at first. I'm betting my answer without concrete code will be difficult for Samir to understand that well. Be happy to talk about this technique in some other setting. And I've said, rarely seen good inheritance hierarchies, very difficult for me to formulate how you can build one. While I don't use inheritance at all, it's still an annoying gap in my modeling knowledge. So I think we could use more guidance here. And Rebecca, again, a very interesting answer. I used to teach how to use inheritance in my OOD courses, object-oriented design. It is a poorly understood skill. And that is why I think inheritance has gotten a bad rap for those who program with objects. The best use of it is to define common behaviors without constraining them overly much, and to provide steps in algorithms that are designed to intentionally be plugged in or ignored. So again, in a few statements, very, very deep. It's a poorly understood skill, has gotten a bad rap. This is why we tend to favor composition. So after these conversations, it was very interesting So for me, I already had my eyes opened about other possibilities for using inheritance. And the next answer is Samir. That's very helpful. I think what you are describing are the two modes of use that I'm trying to hint at. Calling downwards allows for pluggable steps where the supertype acts as a kind of framework. Calling upwards allows for shared behavior as a sort of library. Perhaps the common advice to favor composition over inheritance applies more to the latter. To be honest, I think I've never thought of inheritance as a shared library. I'm thinking about inheritance more as a way to remove duplication by increasing abstraction, which is how we usually remove duplication. We increase the level of abstraction. We find things that are duplicated and we increase the level of abstraction. And in the case of inheritance, you are doing it in a specific way, in a way where you push the interface up and some of the implementation, and you leave the concrete implementation down, which means that a lot of the duplication will be actually pushed higher up in the hierarchy, and this is how you remove duplication. You tend to push it up. The problem is if you push it up too early or in the wrong layer of hierarchy, this is where you start to get problem. And then next answer by Samir. I think what I am suggesting is to decide whether the algorithm lives in the supertype, one algorithm, many pluggable steps, or in the subtypes, many algorithms sharing common code, and stick to that. I found that trying to do both at once and badly. And Rebecca, I suspect that over-abstracting without enough concrete real examples causes much of those problems. Very, very important. I think that one of the main problems we had with the inheritance that I faced, particularly in C++, was this: over-abstracting without enough concrete real examples. So what I find very interesting is that one thing that I've realized is there are two basic approaches to software design. One of them, and both of them, are about finding the right abstraction. What I hadn't realized until now is that actually both of them are about looking at concrete examples and pushing them into the right abstraction. Only one of them is doing this by writing code. It's the test-driven development approach. I write a test that gives me a very concrete example. I write the minimum amount of code that makes it work. I refactor. Then I come with another example. I do more implementation. I refactor. And so on. And while I refactor, I'm starting to see the abstractions getting out of, emerging, although it's not that. It's more like I'm starting to notice common patterns that I'm extracting and that I group together. And the other way is I look at concrete examples and I design classes and actually objects. If you see how Rebecca is talking about this, she's mostly talking about objects in reality. Objects that would have, I'm thinking about the objects that would have these different behaviors, responsibilities, and then I'm extracting abstractions out of those examples. So very interesting. This actually plugs in and shows how close the two approaches actually are. The TDD approach sounds very far-fetched for many people who are used with the other ones, But the problem is that many people who I've worked with, and when we've used this approach, we didn't really know what we were doing. And so we ended up with exactly what she was saying, over abstracting without enough concrete real examples. It's very hard, but this is what you need to do as a designer, to stop yourself, even if you are starting to see an abstractions, wait until you get enough proof that that is the actual good abstraction that you're trying to do. And that's, I think, is a skill that needs more training. And it's helped a bit by the TDD approach, because the TDD approach takes you there little by little. And if you're doing the steps correctly, it's unlikely that you'll over abstract, or at least your abstractions will be more delayed than what I've often seen with this other approach. The problem with the TDD approach is that, so imagine somebody who's very good at this first approach, they can iterate much faster. They can figure out the right abstractions much faster than you're doing it with TDD. So, but in the end, you still need to write tests. So which one is better? Probably both, right? There's no perfect answer. And she continues, the placeholder pattern was intended to be used to put an appropriate hook into your design where behaviors could be extended, but doing that without enough real examples can lead to misplaced, poorly designed hooks. Yeah, and I've seen this. Right, the case I'm currently dealing with, Samir again, and I expect all others I've seen, grew organically, perhaps without any intention of creating a polymorphic design. You've answered my original question. It doesn't sound like such a principle is widely recognized. I think it might have legs, though. I may go reread Genga 4 to see if the subtype polymorphic patterns can be grouped in this way. Well, as I said, there were two. For every Genga 4 patterns, there are two ways of doing that. With inheritance, with composition. But another thing that's very interesting and that I've noticed when revisiting the Genga 4 many years after I read it the first time, and years after I started using test-driven development as my favorite way of incrementally designing things. One thing I've realized is that the way inheritance is used in the Genga 4 patterns, it's very specific. They are using inheritance only in a few very specific ways. It's not the full scope of the relationship. They are just picking precisely the right way in which to use it. And this is what makes these patterns so useful, because you can learn so much from them. And then and one quick thing, since I mentioned incremental design, I used to think until this conversation that the best way of doing incremental design is through test-driven development. Now I'm starting to change my mind a little bit. I think all software design is actually incremental. We just need to recognize that and start from real concrete examples, no matter how we are designing. And just stick to the proof, stick to the actual concrete examples. So Rebecca mentions then, related to this, there used to be informally among us OO folks the rule of 3 heuristic. If you can't find 3 reasonable concrete examples, don't form an abstraction. This is the same rule we are using for test-driven development. You need to see 3 places, duplication in 3 places before extracting an abstraction out of it. And yeah, then there's a bunch of more conversations about this, and about where people have learned about the rule of 3. Willem van der Ende talks about the C2 wiki, very useful resource as well. Jerry Weinberg, another great educator in this area. And so on. So the conversation goes on and on. What's very interesting is that after a while, I found it funny that Samir said, I think it's time for me to start introducing the strategy pattern to functional programmers. This should be fun. Well, the simplest implementation of the strategy pattern is actually a lambda. Think about it. It's precisely what it's about. So maybe it shouldn't be, I don't see how it would be hard, but my guess is, and you can contradict me if I'm wrong, functional programmers tend to be very focused on data. We have 2 general approaches to software architecture and then to programming: data-centric and behavior-centric. You can see it for APIs, right? We have REST APIs, which are data-centric, resource-centric, but resource is just a higher abstraction related to data. It doesn't necessarily mean that there's one table from the database linked to one resource, but you basically think about everything as a kind of data that you act upon. Or you have behavior. And right now, in the world of APIs, we don't have patterns, or there's fewer APIs that are using behavioral style of design. But it's a very valid style. Same thing for architecture. You can have data-centric architecture, or you can have behavior-centric architecture, like domain-driven design. Okay, it's very data-centric. You could go the other way and think about behaviors and how to split behaviors between your modules in an architecture. And if you go in terms of programming, you have data-centric programmers and you have behavior-centric programmers. Data-centric programmers, my guess is that functional programmers tend to be more on the data-centric side, because most of functional programming is about getting data and doing something with it. We have data structures, we have all kinds of fancy type structures, which are basically data, and then you come with lambdas and stuff and apply on them. So very data-centric. Now, I'm not saying that everything that you do in functional programming needs to do data-centric, but my feeling is that most functional programming tend to be more data-centric. And you can also do object-oriented programming in the 2 ways. You can focus a lot on data structures, or you can focus a lot on behaviors. Which one is better? Well, it depends. It depends on the application you are building and on what you like. But the application is also important. So perhaps the challenge here is learning some of the behavioral patterns when what you have is programmers who are data-centric. Maybe that's the challenge. Could be, I don't know. And then, oh, this was very interesting. It sounds to me that the fundamental problem of inheritance, this is what I came up with, is maintaining stable hierarchies, stronger bounds, over time while any of the items can evolve. Seemed to me like the best bet is to have stable pieces of behavior responsibilities grouped in such a construct for it to be stable. So I'm thinking about these hierarchies and how they fit. Graphs, when you have graphs of objects and the relationship between objects are not that strong, it's easier to evolve an object here in some part of the graph without impacting everything. But when what you have is a hierarchy, which is a much stronger relationship, then you might end up with some problems when things evolve. So then it's very important to get the stable pieces in your hierarchy, on the top of your hierarchy, or closer to the top of your hierarchy. And I think this is the challenge with inheritance. And then Rebecca said, I think that calling up or using common behaviors does not imply favoring composition. Composition is best when there are isolated interacting behaviors that are big enough to make a class, a named thing that has some responsibilities. And another factor, composition is also useful when you can plug together composable behaviors. So for example, the strategy pattern strategy objects, or a decorator that has behaviors and delegates. So I tend to think of a composition as a satisfying design tactic best employed when there are multiple possibilities of what can be composed to work together. Yeah, and to me this leads to a lighter, or to a structure that is less prone to issues when evolving. But I still have to have this conversation with Rebecca. I'm incredibly curious what she thinks about that. And then actually the conversation moved into another direction. Steve Friedman came in and asked, why are the actions on an object called methods? Rebecca answered, it all goes back to the name given to actions in Smalltalk. And Alan comes in, we've interviewed Alan as well, and talks about the different methods and so on. So very, very interesting conversation. So if you thought that you have nothing else to learn about composition, or that you should never use composition for, if you have nothing else left to learn about inheritance, and that you should never use inheritance for anything, well, maybe this conversation is telling you otherwise. Or maybe there is a place for inheritance. I'm still very curious what Rebecca would have to say in more depth about networks versus graphs stability when it comes to evolution. My intuition is that graphs tend to be easier to manage when you evolve code, but I could be wrong. So what do you think about all this? What do you think about inheritance? Have you used inheritance? And how have you used it? Do you still plan to use it? Do you plan to actually go and read design patterns once again? Let us know in the comments, or let us know about anything else that you found interesting, or that you'd like to, if you have any questions, leave us some questions. I love comments, so it's great when I find some new comments and I can start a new conversation with you, the people who are listening. Thank you kindly for the view, And until next time, remember to think, design, and work smart.